So as you've guessed tonight, we're talking a little bit about power. This is something that was introduced at a grade 10 level, and we're taking it through the grade 11 and grade 12 levels. So grade 12 is a little bit of revision to get you up to speed. And what I'm going to be doing is I'm going to be talking to you about the ways that power questions are asked during exams. So I've defined it in two separate ways, as the rate at which work is done or the rate at which energy is converted. Now, very often in exams, examiners like to see if you actually understand what you're talking about. Now, they're not going to directly ask you for the power. Very often they'll ask you for the rate at which work is done, and they'll ask you for the rate at which energy is converted. These are two separate ways that they can ask you for power during an exam. Now, I don't want you to get confused because a lot of people see the word work or they see the word energy and they jump for equations which have got those two things inside them. So I don't want you to fall into that trap. So what we're going to do tonight is I'm going to take you through a very typical and very difficult question, because I've received a lot of requests to do incline questions with objects going up slopes and being asked to calculate the power on them. And I'm going to give you a challenge question. But now, the trick to this challenge question is to be able to work at the power in two separate ways. Now, a lot of you are going to work ahead of me and are going to post your answers on Facebook and Twitter, and that's fantastic. This means that you're cooperating and that you're getting to the answer before us, and I want you to check as you go through. Because this question is very, very typical. It's very difficult as well, especially if you're not exactly sure what you're doing and your maths is not that strong. Power is a difficult question. So what I'm going to do is I'm going to put up that challenge question for you. I'm going to hopefully get out of the way, and hopefully you guys at home are going to be able to follow through with that. And here it is. I've got an electric car is headed up a 30-degree incline at a velocity of 20 meters per second, and that is in the direction of upwards. The hill is 300 meters long, and the car has a mass of 800 kilograms. Friction exerts a force of 200 newtons, which is going to stop it slightly. I would like you to calculate the power output of this car. Now, a lot of information going around. I've got an electric car, I've got 30 degrees as an incline, I have a velocity of 20 meters per second of this car, and that's a constant one. And the hill is 300 meters long, and the car has a mass of 800 kilograms. Friction does play a role in this question. A lot of people say, just ignore friction unless they tell you about it. I'm telling you about friction, and that's 200 newtons. I'm going to be able to calculate the power output of this car in two separate ways. Now, my tricks, I don't want you to get too lazy because I do need you to understand both methods of calculation. If I've calculated it one way, I want you to be able to understand it the other way. And one of the things that's going to come up is I'm going to show you both methods. You need to know both of these depending on how they've put the question together. So I've got all my information. I've got my 30-degree incline, velocity of 20 meters per second, a hill 300 meters long, and the car having a mass of 800 kilograms and 200 newtons. So much information. This type of question can get you up to 16 marks. It's very seldom that they're going to give you a question where they just ask you for the power straight away, but I'm going to do this just as a challenge. I know you guys like to know very, very difficult questions, and this is one of those difficult questions. Post your answers on Facebook and Twitter. We're going to be checking in about 10-15 minutes. I'm hoping that people can work their way through this, especially if you work two separate methods. If you've done it one way, challenge yourself and try to find a separate way to get the power output. And hopefully you guys get there before me. I'm going to be explaining for those that don't know what's going on and confirming those which are right. Lots of information. The first thing that I advise that people do in a physics question is to start to highlight or isolate information which is very, very important. So I'm going to go through this with you, and hopefully we can identify which material is actually useful for us. So as you go through your information, I hope you've written this question down, or at least you've drawn a diagram, which is my next step. Let's just take a look at what information might actually be important. I'm going to highlight the numbers and explain why they're important. I've got my electric car. We don't really care what type of car yet. I know that I have a 30-degree incline, so my 30 there is very, very important information. I have a velocity of 20 meters per second. That's worth knowing because my velocity is important for kinetic energy. The hill is 300 meters long, and that's quite important as well because that's my displacement in the same direction as some of my forces like friction. So if I've got 300 meters of displacement and I've got a car which has got a mass of 800 kilograms, that's going to help me in calculating my gravitational potential energy change, or at least my work against gravity. Friction exerts a force of 200 newtons, hugely important. There's a lot of information in front of you. What am I after? I'm after the power inside my question. So I've got a huge amount to go after. And one of the things that I want you to immediately recognize is that they may not actually ask you with the word power. They may say the rate at which energy is converted. Now, if I go back to grade 10, or at least I remember grade 10, power can be defined as the rate at which work is done by work over time. And that's the first approach that I'm going to be taking. I'm going to take work divided by time. But the problem with this is I need to find out how much work is done and how much time it takes to get all the way up this 300-meter hill at 20 meters per second. There's a lot of information. I've got to do 4 calculations before I get there. And I'm going to do them in steps so that you can follow at home and hopefully keep up with us. So let's go about this. The types of work which I can do. First thing I'm going to do is I'm going to make sure that I've got a clear picture of what's going on. I've got my 20 meter per second along the 300 meters. Now there's a couple of other things which I'd like you to put in on your diagram. So we've got our car can move nicely up and down our hill. The question is, what is stopping it and how much mass does it have? I've got a few things which I'd like to add to this diagram, and I hope that you've been watching on my general approach for physics. Always with the diagram, it's simple. My car is not pretty, I'm not an art teacher, and you can see why. But one of the things that I want you to show on your diagram is all the information. It's a great place to collect your info. One of the things that I did know was that my car has got a mass of 800 kilograms. That's quite useful. That gives me a mass, and therefore it gives me a weight and a way to calculate potential energy. What else do I know about my object? I'm being pulled back or held back by a frictional force of 200 newtons. So that's worthwhile putting on my diagram. I've got 200 newtons which is holding me back. Now something else which might be useful during our question is actually deciding which direction might be positive. And one of the things that is very important, especially when working with vectors, is that I've got to decide which way is positive. And I'm going to choose up the hill as positive because that's where my car is moving. That might come into play a little bit later when I choose method 2. So now I've got my information on my drawing. I've put in a positive direction. There's my first D and my second D of my question approach. Physics always requires you to draw a diagram and choose a positive direction, especially with vectors. A lot of people say, do I get marks for collecting my information? The answer is no. But it ensures that I've set up my question nicely and I can succeed that way. Okay, so let's go about my first question. Let's find out how much work is required to do all these things at the same time. I've got kinetic energy from my 20 meters per second. I've got gravitational potential energy because I went upwards. I'm doing work against friction. So there's a large amount of work being done in 3 different ways. So let's start tackling it. The first thing I'm going to do is talk about my change in potential energy. So I'm going to figure out what my change in potential energy is, because that's going to tell me how much work I do against gravity. Because what's going to happen is my change in energy of gravitational potential energy will be work which I have to do. Then I've got to pay attention to my work done on my friction. And you're going to see later on, I'm going to do these separately and put them all together. Then I've got a velocity which gives me a kinetic energy. I'm going to see if there's any change in Ek or delta K. That represents my change in kinetic energy. I have a change in potential, change in kinetic, and work done against friction. These are all types of work which I can do on the object. Well, the power output is all of these combined, and we're going to see what's going on there. Well, let's start off. We're going to calculate the change in potential energy. One of the things that you'll find on your equation sheet is that my change in potential energy is equal to m times g times delta h, which is the mass times by gravitational acceleration times by delta h. So let's see what comes up when we start substituting these values. I've got my mass of 800, I've got my gravitational acceleration of 9.8, and something over here which you might not recognize. One of the things that I'd just like to draw attention to is that I got this whole calculation from the triangle. Some of you are not entirely sure what I'm talking about here. This is my change in height. I've got 300 meters on my hypotenuse. What I'm actually showing you here is a way of calculating the opposite side of my triangle. Because I've got 30 degrees within it, I'm actually calculating the opposite side. This is the important one. I'm trying to look for the height of my triangle. And that's what it is there. My opposite side is calculated by taking my hypotenuse multiplied by sine of 30. If I do all of this together, I will find out that I did 117, I've actually shortchanged myself there, 1,176,000 joules of kinetic energy or potential energy. In this case, it's a change in potential energy. Apologies there. So we've got a change in potential energy, which is work done against the force of gravity. Well, that's part 1 of 3. The next thing which I want to pay attention to is what happens to the kinetic energy. My car definitely has got K or EK, depending on which textbook you follow. Let's see what happens when we start to pay attention to that. Now this one's really, really easy. We were told that I've got kinetic energy because I'm moving. But now what I care about when I'm doing work is the change in energy, or delta K. If I find my final minus my initial kinetic energy, because there was no change in speed, I get 0 joules work done on kinetic energy. That's quite important. I'm just going to stick on that for a second. When we are told that there is constant velocity, my work done or my change in kinetic energy is equal to 0 joules. That's going to come in handy a little bit later on when we talk about the work energy theorem. So now I know that I've got 1,176,000 joules of energy on potential, none on the kinetic. What about the friction? Let's take a look. If I've got my work on friction, I want you to realize that there's a couple of ways of calculating it, but this is by far the easiest. I know that my frictional force multiplied by my displacement, represented by delta x, multiplied by my cos angle over there, and we're going to make a correction there because this is something that mindsetters are inclined to do. I'm going to show you what's wrong with this. One of the things that we see is that everyone substitutes in a 30. I want you to see if you can spot what is wrong with the 30. How can we change this into something correct? Now, a lot of people have taken their slope angle and they've substituted it in. There's my 30, and they've put it in there. Now, work done against friction does not have to be complicated. I prefer to work on one plane. Work done on friction is either cos of 0 or cos of 180. So what we can do is, let's just go back there. Let's just finish off our calculation over here. I can represent it as cos of 180. Please be careful not to use 30. A lot of mindsetters are doing this. And I've seen that they're using the slope angle in the calculation of friction. Remember that we're working on a flat plane. I could have used cos 30 if I was pulling at an angle of 30. This is something I don't want to do, and we've corrected it in the next line as cos 180. I see that I've used 60,000 joules of energy to overcome friction as I moved up that 300-meter hill. Let's see where all these pieces of information come from. My frictional force of 200, my displacement of 300 meters, and my cos of 180, which means that my friction is opposing my motion. Cos 180 just means that I'm moving in one direction. My angle between my force and my movement is 180 degrees, and that's where that 180 degrees comes from. That leaves me with work on friction, which is negative. That's very important because friction actually reduces the amount of energy which I have. And that's going to come into play when we talk about the last little piece. Method 1, I'm pretty sure you can see, is very lengthy, but I need you to understand each little calculation that I'm doing. I calculated work done against gravity, which was potential energy. Work on kinetic energy was 0. My work on friction giving me negative 60,000 joules. Now what we're going to do is we're going to see what happens when we add all of them together. And the way in which we add them all together is usually 4 marks. Be very careful about how you set up this next piece of work. Let's take a look there. Now, if I use the work energy theorem, generally I'm set up for success. My change in kinetic energy is equal to the work done by my net forces. Now, work net is comprised of a couple of things, and I'm going to show you just what I mean by a couple of things. Now, there's a lot of information here. I'm going to take you through it in bits and pieces. I told you that the change in kinetic energy was 0. I've got my work done against gravity, my work done by the applied force, which is something that a lot of people forget about, and then my work done by the frictional force. The question is, which work am I after? Well, I've got my delta EK, I have my work on gravity, I don't have my work done by the applied force, and this is the thing which is going to get me the power. That's the work which gives me the power output of whatever's powering that car, in that case, an electric motor. My work done on friction is in there as well. Something which I want you to pay attention to is how these types of work affect the amount of kinetic energy that your objects have. You'll see that I've substituted in my work against gravity as a negative number. That means that work done against gravity has a negative effect on the kinetic energy. Going up a hill, gravity slows me down. My work done by the applied force, we're not entirely sure, but we think it's a positive type of work. Work on friction generally will always have a negative effect on K, my kinetic energy. So if I've got negative work which is being done against gravity, against friction, those are going to be negative numbers because they'll reduce the amount of K. And that's how I know to put in a negative or a positive. This allows me to get the work done by the applied force. So what we're going to do is we're just going to shift that up slightly because I want the mindsetters at home to actually see this. Because I've got 1,236,000 joules of energy done by this engine. Okay, so I've got work done by the applied force, but we're not done yet. A lot of you are screaming and your brains are busy exploding at home. There's a lot of work done in method 1. Method 1 is by far the most complicated way of working out power. And most of you have figured out that we haven't actually calculated power yet. All that I've got is work done by the applied force, which is step 1. I've calculated all of this, done the work energy theorem, I've reinvented the wheel, but I haven't got power yet. The problem is your examiners expect you to understand each and every step. Work done against gravity is your change in potential energy, negative. What about your work against friction? That's a negative form of work. If you have a constant velocity, your change in K is 0. So I've got my work done. Let's see what the rate of work is done. Anytime you hear that word rate, that means divide by the change in time. That's one of the last steps, and let's move there. So I've got to find the time quickly, and one of the things that I've been able to see is that if I've got a displacement of 300 and I divide it by my velocity of 20, I'm going to be left with a time of 15 seconds. So let's pop that into an equation. I'm sure that people at home can do this for themselves. If I take my 1,236,000 divided by 15, I'm going to get an answer here of 82,400 watts. That means 82,400 joules every second. That's how fast work is being done or energy is being converted. So one of the things that they'll very often do is they'll actually change your unit, and I'm going to do exactly that. Very often they'll actually quote that in the non-SI unit as 82.4 kilowatts. So they can do that sometimes, and they do expect you to know this, but they want your answer in watts. And be careful that this W is a unit. It's not work itself. Now, this took forever. One of the things that I would say to you is try not to use this example or this particular method in an exam unless you're told to, because sometimes it's actually possible to do it in another method which is way, way, way shorter. And that's what I'm going to show you now. Method 2 actually uses a new equation which is just for the grade 12 syllabus. Everything which I've done here, I could have actually done with grade 10 and grade 11 theory. Now, I've found the change in potential energy which gave me the work against gravity. I found that there was 0 change in my kinetic energy. I found that there was work done against friction with 60,000 joules of it. I added them all together in a very complicated way inside the work energy theorem. Now, that was a very complicated way to find my work. I then further had to go find the time as well and then put them all together. So I had like 5 calculations to arrive at this one answer. I'm going to show you how to do it in 2 or 3 steps. But this does require that you draw with me, that you work with me. Method 2 is coming up. So let's see how I set up method 2. Okay. Now, if I start to think about my grade 12 syllabus, I've been told about a different formula. I'm actually going to move around my formula and we're going to work with this. That power is equal to the applied force multiplied by the velocity. There's a couple of problems with this particular one. And I'm actually going to hide away some of this stuff from you. And we're going to work through this in a moment. I've got it worked out. And if you're confident in this, you can check your answers as we go. but this is going to be a little bit confusing unless I tell you what's going on here. We already know that P for power is equal to the force, and this is force applied. So this is the force applied multiplied by a velocity. The problem is that there is only one velocity, and this is usually your average or your constant velocity. That's the only time that you can use this equation, is if I have a constant or at least an average velocity to work off. So if I've got my force which is applied with my velocity, I can get power straight in one step. The problem is getting the force applied. Now I'm going to show you. There's a couple of things over here which are a little bit confusing. I'm going to move them out the way in a moment, and let's actually make a little bit of space there. Let's move them. And we're going to find out, where do I get this force applied? And the answer lies inside vectors. Remember that if I start taking a look at my equations where I had the whole thing described, I had a resultant force of 0. Question is, how did I know that? One of the things that I was told very early on was that I had a constant velocity. Now from grade 11, I'm told that if I have a constant velocity, I have equilibrium. This means that my resultant force is 0. So that's a good place to start. But the question is, what goes into my resultant force? And for that, I need to start drawing. I'd like you to draw with me, and we're going to see what's involved inside this. There's a couple of forces. So I hope that you can actually identify your forces. Let's start drawing in a color which you can actually follow. I'm finding that the black is probably not going to work, and let's start out with that. Let's select, there we go. Okay. Alright, so if I've got my slope, one of the things that I have to do is start drawing a free body diagram. Remember that a free body diagram, you represent the center of the object as a dot. So there I've got my dot, and I've got the forces which I'm going to represent. Now the force applied was driving the object forward, and that's the one that I want. My force applied is quite important. What about the other forces? Well, I already know that I've got a force of friction which is holding me back. That one's quite easy because I was told that that was 200 newtons. What about the force of gravity? Now, it's not very useful to talk about forces which are not acting in the same direction, or at least on the same plane. I've got these two diagonal forces. I don't want to go put in a force which is acting vertically. I'm going to show you what not to do, then I'm going to show you how to fix it. One of the things that I see learners do, and they say, well, I've got a free body diagram, let's calculate the force applied. There is my force of gravity. That's not very useful. I can't add these forces up directly. I need components which are acting in the same direction. So what I'm going to do is I'm going to find the parallel component of force of gravity. So let's undo the mess. Let's take away our arrow because it's not meant to be there. So what I'm going to show you now is how to calculate the force of gravity but parallel to the slope. If I've got just the parallel surface over here, what I've got to do is I've got to resort to a little bit of trigonometry. I see that this is acting in a triangular form. If I've got force of gravity which is acting downwards, I've got to find out how much is acting in the same direction as force friction. And one of the shortcuts that you'll learn is that I take the mass multiplied by gravitational acceleration multiplied by sine of the slope angle, which was 30 in this case. That is the force of gravity, or at least the part of gravity which I'm particularly interested in. I'm not interested in the vertical part. That's not very useful to me. I cannot use that. All that I can use is already here. Something else important to do whenever you're doing one of these free body diagrams and you're talking about F-res is to put in a resultant force. So I'm going to place a resultant force and a positive direction on this. Well, we're not sure which direction my resultant force is unless we actually think about it. We had a constant velocity. That means that F-res was 0. So this is the place where I start. So let's take a look at our calculation. Let's move it a little bit upwards. Let's move that out there. And let's actually shift this up into the place where we can see it. So if I start out that F-res is equal to 0, meaning that I have 0 resultant force, what I'm going to do is I'm going to follow through and we're going to go through this slowly together. You might have written this down, but it's not making any sense yet to you. remember that when I put together a resultant force, I need to assign the sign for the force. Is it a positive force? Is it a negative force? You can do that on your diagram if you'd like, and we can do that together. So if I went to my diagram and I said, okay, well, force of friction is acting down the slope and is therefore negative. What about my parallel component of gravity? That's also negative. Let's just make sure that we're keeping it in the same color so that you can identify what we're doing. I know that these two forces which are pushing downwards are negative. So if I put together all of my forces inside my F resultant or resultant force, I see that friction is a negative force. I see that gravity is a negative force. My force applied is positive. The trick to doing vectors is always the signs, choosing a positive direction and sticking to it. So let's go through this. Let's actually see what's important. Let's see what I've got. I've definitely got my force of friction. We can substitute that in. That was given to us. If I move onwards, my force of gravity, my mass multiplied by gravitational acceleration, as long as I'm on Earth, I've got that, and my slope angle is done. My force applied is the only thing out of there which I don't know. I know that all of this adds up to 0. I'm going to make a little bit of space and just get rid of some of our drawings over here because this is a little bit messy. And let's just clear some space and make sure that people can see what I'm calculating here. So I've got a couple of things inside here which are important. I knew that I had 0 resultant force. I've got my force of friction, my force of gravity that I'm acting against. Then I substitute. Out pops a force applied, which is great. I knew that I had my negative 200. There it is. I knew that I could substitute in my mass, my gravitational acceleration, and my slope. So there it goes. So I've got my substitution going in. Okay. All right. Now all that's remaining is my force applied. I've got everything. I definitely have everything that I need. The only thing which comes out is my force applied. That's what I need for my power equation. The last thing that I need over here is my velocity. So if I put all of this together, I've got my force multiplied by my velocity, and I can get my power which comes out of there.